Hello everyone, welcome to Gate Pass. In this video I am going to take problems related to thermodynamics that appeared in Gate paper of 2007. So the first problem which I have selected, it consists of a binary mixture made up of methanol and water. So I am going to label methanol as component 1 and water as component 2. Now the vapors of this mixture are in equilibrium with the liquid, okay, at 60 degrees centigrade and 60 kilopascals. Further, they have said that the mole fraction of methanol in liquid phase is 0.5 and that in the vapor phase is 0.8. Further, they have also given you the vapor pressure of methanol and water at 60 degrees centigrade, and they have asked you to calculate what is the activity coefficient of water in the liquid phase. They have asked you to assume that the vapor phase, it behaves as an ideal gas, so that means your fugacity coefficient is equal to 1. Okay, so straight away you know that this problem will be solved using Raoult's law. So since we have to find out what is gamma 2, so I am going to write down my Raoult's law for component 2. So total pressure multiplied with the mole fraction in the vapor phase, that is equal to mole fraction in the liquid phase multiplied with vapor pressure and multiply it with your activity coefficient gamma 2. Okay. Now let's see what are the variables which we know. The total pressure is 60 kilopascals. Okay. So 60 into 10 raised to 3. Y2, since I know Y1 is 0.8, so Y2 is 0.2. Okay. Now X1 is 0.5, so I also know what is X2. It is 0.5. P2 saturation, that means your vapor pressure of water at 60 degrees centigrade is given as 20 kilopascals. So multiply it. And the only unknown in this equation is now your gamma 2. So very straightforward problem. If I solve this, I get gamma 2, that is equal to 1.2. Let's see which of the options is correct. Option B is correct. Okay. So this was a very simple problem, again based on Raoult's law. So you will see there are several problems in GATE exams which are based on Raoult's law. Next, let's move to problem number 77. With the same data set, they have asked you another question that you have to find out what is the excess Gibbs free energy in joules per mole of the liquid mixture. Okay, and for this you just need one information or one equation, which is that your ln gamma 1, it is a partial molar property with respect to GE by RT. What it means is that if you take a partial derivative of GE by RT with respect to your N1, okay, while keeping your temperature, pressure and all other N constant where J is not equal to I. Okay, so your ln gamma 1, it is a partial molar property with respect to GE by RT. Okay, so if this is a partial molar property, I can straight away go ahead and apply my summability relation to calculate the mixture property. Okay, so if I want to calculate my GE, let's say I am going to write it now in this form, GE by RT, then it will be equal to x1 ln gamma 1 plus x2 ln gamma 2. Okay, because these are partial molar properties with respect to GE by RT, so I am straight away writing it. Okay, so this is by summability relation and you have seen it several times. So now the remaining thing is very simple. You have to find out what is gamma 1 again by using Raoult's law, and then plug everything in this equation and find out what is your GE. Okay, so let's do that. So first we will find what is gamma 1, that will be equal to, if I rearrange my Raoult's law, what I get is total pressure multiplied with your mole fraction in the vapor phase divided by your mole fraction in the liquid phase and multiply it with P1 sat. So your gamma 1 will be, let's say what is total pressure, 60 into 10 raised to 3, Y1 is 0.8, X1 is 0.5, and your vapor pressure P1 saturation is 85 kilopascals, so that's why it is multiplied with 10 raised to 3. So if I do the calculation, I get the answer for gamma 1 as 129, I am going to write it as 1.13. Okay. Now I will write GE by RT. So I will take RT on the other side, multiply it with x1 ln gamma 1 plus x2 ln gamma 2. This is nothing but your rearranged form of summability relation because I have to find out my GE. Okay. So R is 8.314. What is temperature T? Always remember to convert your degree centigrade into Kelvin. So your 60 degree centigrade will be equal to 273 plus 60, that is 333 Kelvin. Okay. X1 0.5 into ln gamma 1. Okay. So ln of 1.13 plus 0.5 into ln of 1.2. Okay, solve this and you will get the answer in joules per mole. Okay, so if I solve this equation, I get the value as 421.56 joules per mole. Okay, now what I will do is I will just round this off and see. Okay, so I can take it equal to 422 joules per mole by rounding it off, and I see that my option C is the correct answer. Okay, so very simple problem. The only things which you required were your modified Raoult's law and your summability relation, which we have seen several times till now. So the next question which I am going to take, it is problem number 33. It says that you have 2 kg of steam at 400 kilopascal and 175 degrees centigrade in a piston cylinder device. Okay, so this is a closed system. Now it undergoes a reversible isothermal compression to a final pressure such that the final state of the steam is saturated vapor. So you are starting with superheated steam and after compression you have saturated vapor. Okay. So they have asked you to calculate what will be the work done for this process, and the data which is given over here is that you at 175 degrees centigrade and 400 kilopascal, they have given you the values of specific volume, specific internal energy and specific entropy, okay, for the superheated steam. And similarly they have also given for saturated vapor at 175 degrees centigrade, specific volume, specific internal energy and specific entropy values are given. Okay. Now you have to find out what is the work done for the process. So since this is a closed system, I am going to write down my first law, which takes the form delta U is equal to Q plus W, where my sign convention is that heat supplied to the system is positive and work done on the system is positive. Since we are compressing, we are doing work on the system, so I am interested in finding out what will be W. So let's rearrange this equation. So W will be equal to delta U minus Q. Since this is a reversible process, I can also write down my Q as delta U minus T delta S. Okay. So in this equation, I can calculate what is delta U and delta S from the data set which is given. Okay. So W, that is equal to, let's say my final condition is 2 and my initial condition is 1. Okay. Then I can write delta U as U2 minus U1 minus T times S2 minus S1. Okay. So I am going to find out what is the work done per kg of steam, because here I am using specific quantities which are per kg. Okay. So now what I am calculating is work required per kg of steam compressed. Okay. So let's first find out what is this and then we will multiply it with 2 to get the final answer. Okay. So what is your U2? Let's see, 2579 minus U1, that is 2606 minus T. What is T? That is 175 degrees centigrade. Don't forget to convert always your temperature in degrees Celsius into Kelvin. So when you convert it, just add 273 to it and you get 448. Okay. So this is 448 times, what is S2? 6.622 minus 7.055. Okay. So when you do this calculation, what you get is that the answer which you get is 166.98 kilojoules per kg. This is the work required per kg of steam. Since we are compressing 2 kg of steam, so I will find out the work required by multiplying this quantity with 2. So if I multiply this, I get the answer as 333.96 kilojoules, or I can round it off to 334 kilojoules, which is the required answer. Okay, so the next question is question number 31. They have said that for a pure substance, the Maxwell's relation obtained from the fundamental property relation du is equal to TdS minus PdV is which one of the following? So I have told you that there is no need to remember all these equations, Maxwell's equation, because you can derive it directly then and there from this equation. And I have also told you how to write down these Maxwell relations using a shortcut in my very first video, where I am discussing the problems of GATE Thermodynamics year 2022. But I will just recap it. Okay, so there I have talked about legendary transformation, and from this equation you can also write down the equations for change in enthalpy, change in Gibbs free energy, and your change in Helmholtz free energy. Okay, so you go and check that video, but here I will tell you, okay, how to write down once again the Maxwell relation if the fundamental property relation is given. Okay, so what I will do is I will take the partial derivative of this coefficient. Okay, so del t with respect to del v. Okay, and I will keep this s constant. Okay, and that will be equal to minus, take the differential partial derivative of this coefficient with respect to this variable, so it will be del s, and then hold this variable constant. Okay, so this is how you can write down very quickly what are your Maxwell relations. You do not have to go and take the derivative of these twice and then equate it. Okay, that will waste your time. So this is a shortcut. Remember that. I can directly write del t by del v at constant s, that is equal to minus of del p by del s at constant v. Okay, you can do this with other equations as well. So I will write down the Maxwell relation for one other equation, but let's see first of all which one is correct. So your option A is correct. Okay, once again I will show you how to write down Maxwell relation using one other fundamental property relation. Okay, so let's write down what is dg. I have told you that when you obtain G, what you do? You do the legendary transformation. You convert your variable S to T and your V to P. Okay. So in that case, how do you write down dg? What I do is that I switch the variables. So I will write it like this and put a minus sign over here. Okay. Again over here, you will switch the variable and change the sign. Okay. So this is your equation for dg, that is equal to minus sdt plus vdp. Now let's write down one more Maxwell relation, okay, based on this equation, just for practice. Okay, so the coefficient is minus s, so I am going to take the partial derivative of this with respect to the other variable, that is p. So minus del s by del p, and what I will do is I will keep this variable constant t. Then it will be equal to, now take the partial derivative of this coefficient del v with respect to this variable, okay, del t, and what you will do is keep this variable constant. Okay, so this is how you can quickly write down your Maxwell relations. Okay, so the next question is question number 30. The system goes from state A to state B via two paths. One is irreversible, the other one is reversible. Okay, now it says that to change the state of the system from A to B, okay, which one of them is the correct option? Okay, so it's just based on your definition of your path functions and state functions. You know that your Q and W are path functions. Okay, that means that they depend on the path which it follows. Okay, and your change in internal energy. Okay, your U is a state function. Okay, So in this case, you know that delta U, Q, W are same for the two paths? No. Q and W are path functions, they will change. Okay. Q and W are same? No, these are path functions, they will change. Delta U, Q are same? No. Q is a path function, delta U is a state function, it will be the same for both the paths, but Q will be different. So this is also wrong. In this case, option B is correct, which says that your delta U is same for both the paths, okay? Whether it is reversible or an irreversible process, if the system is going from state A to state B, the change in the state functions will remain the same, okay? So your option B is correct. So I hope that you liked my teaching, and if you really like this video, please don't forget to subscribe to my channel and hit the like button. And once again, thanks for watching.